All right. Should we start a new topic? These are all topics that are required for this course. And sometimes I've had 5 billion slides and people barely understand it. And then I have a fewer slides and people barely understand it. And now I'm trying a new version. Well, this version isn't that much different than the version that I have before. But all it does is bang, bang, bang. It does the logic. All right. We try to do minimal sort of fluff in between, and let's see whether you can follow it. All right. So what we're trying to prove is what Turing proved is that there's some uncomputable problem. So the problem in question is the halting problem. So here we can ask, right? I guess I don't say the halting problem, but suppose I gave you this input. I gave you this algorithm here. Does this code halt or does it not halt? And you'll say clearly it halts, right? It loops, it runs. In fact, you can tell me it runs 1,000,000 times. All right, what about this algorithm here? Does it halt? And you'll say clearly it doesn't halt. Why? Because it loops for all values of A. All right, here's another problem, right? It loops over all integer values, positive integer values of A, B, C, and Z, and it stops when this relation holds. Anybody know whether this program ever halts? Well, it turns out that Fermat had a theorem called last Fermat's theorem, and he didn't actually prove it. He said he knew the solution, but he didn't. And it took hundreds of years for people to prove it. And it turns out that it is true that there are no settings, there are no integer values bigger than 2 for which this is true. So this program will never halt, right? But just asking, does this program halt or not, took mathematicians hundreds of years, right? So that's just, it's hard. And in general, what is chaos, right? Chaos is still deterministic, right? People might think chaos is random, but it's not random. It's very deterministic. You tell me the initial conditions and you can crank forward and see what would happen, right? But the problem is, because what will happen is very bizarre and small changes to the input will change the output, that you can't know what it's going to happen. The only way you can know what will happen is by running it and seeing whether it happens, right? So if you want to know what this program does, is you can just run it. And if it halts, you can then say, hey, I know what it does. It halted, I know what it does. But if it keeps running, how can you know it will never halt, right? You can't run it. You can't run it forever and say, hey, it never halted, right? Here's another sweet little program, right? Here, I set some value for C, and and it's a complex number, right? And I want to know, will this program converge to one number or not? And so that is very complicated, right? Here, if my C is a complex number, so here the real part is along here and the imaginary part is along here, the black regions are where it converges to one number, and the blue numbers are where it goes into complete chaos. And in between, maybe it flips between 2 numbers or 3 numbers. So it's a beautiful fractal, right? So whether programs halt or not is a complicated problem. All right, so in 1920, Hilbert in Paris asked, does every problem computable or some problems uncomputable? And Turing defined a Turing machine, and Turing proves that the halting problem is undecidable. There's no algorithm to solve the halting problem. All right. Everybody get what we're doing so far?
Yes.
All right. So we're going to all do it in terms of first order logic. So let's make sure we have the logic down. What does it mean for a computational problem P to be computable? It means there exists an algorithm or a Turing machine. There exists a Turing machine such that the machine computes the problem, right? That's what it means for it to be computable, is there's a machine that computes it. Well, what does that mean? That means on every input, it gets the right answer. What does that mean? That means the machine on the input gives some answer, which might be it halts and says 5, or it might run forever. And then P has to be the same answer. P has to say the problem is requiring the input, the answer to be 5. So then the machine has to say 5. Right? Everybody understand computable? And P is never going to say run forever. So M always has to halt. Right? For this to be true, there has to be a machine such that for every input, the machine halts and gives the right answer. All right, so and how do we play the game? Well, I want to prove that there exists a machine, so I give you a machine. And then the adversary wants to prove that my machine doesn't work. So the adversary gives me a worst case input, right? And then we check to see whether my machine gives the right answer on that input, right? And that's computer science, right? That's what we've been doing all along. Everybody understand that? So uncomputable is you just take the negation of it, right? If it's not true that there exists, then for every machine, it's not true, right? If it's not true for all inputs, then there exists an input for which it's not true. So we just took the negation. And how do we play this game? How do we prove that a problem is not computable? Well, the adversary, it's a for all. So the adversary gives me an arbitrary Turing machine, right? And I want to prove that this Turing machine doesn't solve the problem. So how do I prove it? Well, I take the adversary's Turing machine and I have to come up with an input. And what do I have to do then? I have to show that that the Turing machine in question doesn't give the right answer. Why? Maybe the Turing machine in question runs forever on this input, or maybe it stops, but it doesn't give the right answer, right? So that's what we have to prove. Everybody following that? Everybody
Yes.
good? All right.
Good.
Now this is very hard to do in general. It's hard to prove things aren't computable. All right. Now, you ready for magic? We're going to just give you some absolute magic here. We're going to, in 1 or 2 slides, we're going to prove the following statement. We're going to just prove that there exists a problem, some weird problem, computational problem, that is uncomputable. Right? So how do we do it? Well, it starts off with exists. So the prover gets to come up with the computational problem, right? And if you go to my other slides, I have lots of slides discussing why we came up with this problem, all right? But I'm not going to do that now. I'm going to just tell you what the problem is, all right? And how do I tell you define a problem? I have to say for every possible input to the problem, what the required output to the problem is, right? So let's do that, right? I'm going to come up with a computational problem, right? So for every input, I have to define what it is, right? Well, if the input happens to look like a Turing machine, the input it looks like a description of a Turing machine, then the required output, then I can ask, what is the required output of my problem on this input that happens to be the description of a Turing machine? And what's the required answer? Well, you take the Turing machine that we're talking about here, and you run it on a description of itself. And then what do you do? What's the required answer for P? Well, it's anything different, right? Anything different at all, right? So this is a well-defined problem. So let's discuss it for a minute in case you're nervous, right? What does it mean to take a Turing machine and run it on itself, right? Well, people sometimes, when they look at things having self-reference, they say, oh, new agey things are all about self-reference, and they put a lot of meaning into this. But don't put it too much meaning into this. This is just a proof, and we could design the proof to be different. But anyway, what is a compiler? A compiler is an algorithm, and you could use the compiler to compile itself, right? Or you can use, what is an editor? It's a piece of code. And you could use the editor to edit the code of the editor, right? So here, we're computational problem P, you give it the description of a Turing machine, and you could ask the question, what does that Turing machine do on itself, right? You could ask that question. And then the required answer for P is to do something different, right? So what I haven't said is, suppose problem P, you give it an input that doesn't look like a description of a Turing machine, and then you could define the output of P to be anything you want. You could have it just say, yeah, okay, that's not a Turing machine. Right? Everybody understand my problem P?
Yes.
All right.
Sorry, I actually didn't get it. Could you go over it again?
All right. So here, let's do some examples. Suppose problem P is given a Turing machine, right? And what does that Turing machine do? If you run that Turing machine on a description of itself, then what that Turing machine does is it says, it outputs, I love myself, right? Why? You gave it a description of itself, and so what it did is some Turing machines, if you give them a description of themselves, they say, I love myself, right? And so what does our problem P do on that, a description of such a Turing machine? It needs to do something different, right? So maybe it will say, I hate myself, right? Does that make sense?
Yeah, but in the best case, isn't it to say I don't love myself?
Yeah, you just have to do something different. So yeah, I'm
Okay,
just saying that's just different than that.
Okay.
Doesn't matter how it's different, right? Here's another example. Suppose you have a Turing machine, which you run it on itself, what it does is it runs forever, right? So what does M require? Well, what does P require? Well, P requires that when you give it that description, it does something different. And maybe what it does different is it requires that it halts and laughs, right? Just something different. Right? Right, so
Thank you.
So when I describe a problem, right, suppose I describe the square problem. I'm saying if the input is 5, what you should return is 5 squared. If the input is 8, you should return 8 squared, right? So here I'm defining a different problem. This problem, you give me a description of a Turing machine, and I tell you what the required output is, right? The required output is to do anything different than that Turing machine does on itself. All right, everybody understand what this problem is? Why don't we go forward and see how we use it? All right. I'm claiming that there's no Turing machine that can solve the problem, right? There's no Turing machine that can compute P, right? I want to prove that. So how do we prove that no Turing machine can compute this problem P? Well, I have my adversary give me an arbitrary Turing machine, right? All right, great. Now, I'm claiming that the Turing machine that the adversary gave me doesn't work. Why doesn't it work? Is because I'm going to come up with some input on which it fails to work. And I just use the notation I sub m. Why? Because my input will depend on the Turing machine you give me. If you give me a different Turing machine, there might be a different input on which it doesn't work, right? I just have to come up with, for each Turing machine, I have to come up with one input on which that Turing machine doesn't work. And so I'm just calling that input I sub m. All right, does that make sense? I have to come up with an input. And what input am I going to come up with? Well, I'm going to come up with the description of the Turing machine that the adversary gave me, right? The adversary gives me a description of a Turing machine, right? And claims that that Turing machine solves the problem hard. And so what I do is I say, ha, your Turing machine doesn't solve P. Oh yeah, why not? Well, it doesn't solve P when you give it a description of yourself. Why is that? Well, let's just check. Well, you take the adversary's Turing machine, what does it do on itself, right? That's what we're asking. We have a Turing machine and we want to, what does it do when I give it an input? Well, what does it do when you give it my required input? Well, P is designed so that given any Turing machine, the required output is anything different than what the Turing machine does on itself. Right? Does that make sense? And that's it. That's the entire proof.
This feels like cheating.
Yeah, it does feel like cheating. And yeah, and poor Gödel, he worked really hard to prove Gödel's incompleteness theorem, and this proof is so much easier, right? It's just bang, bang, we proved it. Does it feel like cheating? Yeah, it feels like cheating, but there you have it.
So, but how would you go about a proof like this if you come up with a different p hard? Like,
all right. Well, we didn't have to. We just right now we had to come up with one problem that was uncomputable, right? But so now we just proved that p hard is uncomputable, right? So, well, what we care about is the halting problem. What is the halting problem? Is you give it a description of a Turing machine and you give it an input and it tells you whether that Turing machine halts on that input, right? That's what we, so let's go the other direction, right? Let's see if we can compute p hard, right? Let's just try to come up with an algorithm for p hard. Well, what does p hard do? Well, you're given a description of a Turing machine and you kind of want to know what does that Turing machine do on itself. So what's the obvious algorithm is you run it, right? You're given a Turing machine, you just run it. But the problem is if that Turing machine runs forever, then you will never stop, right? So here's what we're saying is suppose we have an algorithm that solves the halting problem, right? I'm going to now give you an algorithm that solves p hard. All right? What is the algorithm? Well, actually, this is saying there's not an algorithm for p hard, and hence there's not an algorithm for the halting problem. This is a reduction, just like we did before, right? We proved that there's no algorithm for the hard problem. So then we proved if we could solve the halting problem, then we could solve this weird hard problem. But we can't solve the hard problem, so we can't solve the halting problem. And that proves that the halting problem is undecidable. All right? People following that part? So now I'm going to give you an algorithm for solving P hard, right? You're all computer scientists, so this is just going to be an algorithm, right? Takes as input the description of a Turing machine. And what does it do? Well, it has this program halt, right? And halt always halts and tells you the right answer. So what do you ask halt? You ask halt, hey, I have this M and I want to know what M does on itself, right? So does M halt on itself? And if it says that no, M doesn't halt on itself, then you know what the Turing machine does, and so you can get P hard to do something different, right? But if it tells you that M does halt, right? If M does halt, then you can run M on M. And that's not scary. Why? Because you know that M will halt. You've been assured that M will halt, right? So you run M on M, and then you just do something different. If this tells you that M runs forever, then you do something different. If this tells you that M halts, then you run M on M, find out what M on M does, and you return something different, right? So there is an algorithm for P hard, right? But we proved that there's no algorithm to solve P hard. So that means there's no algorithm for solving the halting problem. Right? Are people getting that? So you were asking, hey, can I come up with a different problem? And we're going to come up with whole lists of problems that are uncomputable. But they're all going to be solved, reduced to the halting problem. From now on, we're going to say, hey, I'm going to come up with a new problem I think is kind of cool. But if I could solve that problem, I could solve the halting problem. And I can't solve the halting problem, so I can't solve this weird problem. Right? So here's another example. Here's a problem called math truth, right? What do you give it? You give it a logical sentence with for all that exists over the integers, right? The universe is the integers. We have the usual plus and times. And I want to know, is alpha true in that model, right? So remember what we proved a couple days ago, last week. We proved that there is this weird, for every Turing machine, right, there's a sentence that says, hey, my Turing machine will halt, right? And so this sentence will tell me whether or not it's true, right? If you plug this sentence here, first order logic sentence is true if M halts, and it's false if M doesn't halt. So if I had an algorithm to tell me whether or not a sentence was true, then I would have an algorithm whether or not a Turing machine halts. But I don't have an algorithm whether a Turing machine halts. So I don't have an algorithm for the truth problem. Right? Does that make sense? So those are 3 computational problems that we don't have algorithms for.